Hi, this is Grover with Blue Collar Codes, Quick and Dirty, episode 30. We're going to go over heaps. If you wish to follow along, link in the video summary. So I'm going to go over two visualizer tools, complements of Claude, and then we're going to go over a Python implementation utilizing an array as a container. So to dive in, a heap is a binary tree that is balanced and that satisfies what are called like the heap order properties. In this case, we have a max and a min heap. The max heap order property is that the parent nodes are larger than the child nodes. And remember, a binary tree means that each parent node can only have at most 2 child nodes, and what it means to have a balanced or complete binary tree means that it's filled from top to bottom and then left to right. So at each level, you're starting breadth first from left all the way to the right, filling every node in that level before you go to the next level. And so when you insert a value in this outline here, what it's going to do is it's going to fill it out at the 10 and add a value there. And what's unique in the heap is that when you're inserting a value, you're going to be inserting it there whether or not it satisfies the heap order requirement. And then what you're going to have to do is compare upwards to make sure that it is being satisfied, and that's called bubbling up. And to kind of envision the bubble down when you extract a root, think of a doubly linked list structure where you're maintaining a reference to the root node and then the last inserted node. What they're effectively doing is you're removing the node at the root, replacing it with the node that was last inserted, the tail, updating all those references, and then from there you're doing a comparison downward and bubbling down that value until the max heap, in this instance, the max heap order requirement is fulfilled. And a min heap is just the opposite of a max heap in that all of the parent nodes have to be smaller than their child nodes. So this was kind of more a class implementation, class node implementation using a doubly linked list. Let's look at what an array implementation entails. So in this, when you're implementing a heap in an array as a container, you just need to keep in mind these three main equations. To find the index of a parent node, you are putting in the index of a child node through this equation. And then to find the left child of a parent node, you're putting in the parent node's index into this equation, then you have the left child, and so on and so forth. So just to showcase this and give you one example, let's click the 12 in this case. You have index position 2, and so you have 2 times 2 plus 1 equals 5, and then voila, you have 5 is the left child of the parent node 12 at index position 2. And then the right child, of course, you add 1 more because you're adding 2, and that's 6. So let's go over a Python implementation of this type of structure. So we are actually having implementation of the min heap. So before I start stepping through it using the debugger tool, let's just go over a few items. You have a nested class called item that within slot attributes it has a key and a value, and then you have an overloaded operator that allows you to compare the keys between these class items. Some of the noteworthy methods here are the parent, which is the equation to find a parent based on an index, and then the left child based on an index, and the right child based on an index. And then you have two methods that are making sure that anything you're checking is within bounds of the overall length of the array. If the values are not in the correct heap order property, meaning a min heap order property, you have a method to swap out values. And then you're continually swapping things recursively when applicable until everything is in the correct order. And within the constructor, I am inputting this list of tuples that are basic integers and then data pairs. in the form of characters. So, just of note, the main thing that you're ordering in a heap structure is the key. So you're organizing the key based on the min heap property. And then the contents themselves, like the values, are never touched. At least not during the organizational process of making the structure. So let's dive in and go over making the structure with this implementation. So I'm going to step through to a portion where it's actually being constructed. We'll step over that. So it's basically taking the self.data and it's just putting the key value pairs into a class item instance and then just populating an array straight up. If it's less than one or if it's one item, it's not going to do anything because that's just the root. Otherwise, it's going to heapify, and that's what we're going to go into. So keep note of the windows up here, the variables on the left-hand upper window, and then you have some extra watch variables that I put in here so you can kind of better understand what this down heap is comparing at times. Just because it's making a lot of comparisons, jumping up and down, jumping around, and I'm just going to go through it once briefly, and then you can always get this file and go through it more yourself to if it's a bit more confusing. So here you have the overall length of the index, which I just wanted to have that item there so you know that the last index position of all of the variable the data points we have is 10. It creates a starting point, which ends up being the first parent whose children are going to be the end of the array. And that's what I wanted to showcase here, is that the start is actually the overall list divided by 2 in floor division, then subtract 1. That's where you start. And when you do the math behind that, the left child and right child end up being the last 2 positions of the array. So as you can see here, you have J, so the first parent node we are going to be checking is 4, because remember, this array has already been populated. Now we're just rearranging it to make sure that it satisfies the heap order property. So you have the parent at node or index 4, then you have the left child at index 9, the right child at index 10. I thought that was pretty clever and cool. So let's dive into a little bit how it's making these comparisons. So here, what we're doing is not comparing anything right away as far as the keys themselves. What we're doing is we're just preparing the calculations for the indexes for the left and right childs for the position J. In this case, it's position or index 4 for the parent, and then 9 and 10 already. So it's going to be jumping around a bit going to this left. I will stop it when we get to something more important. And now here we have the first important comparison. It's basically comparing the actual keys now between the right and the left child. So what is smaller? It's going to see if the right child is smaller, it's going to define this small child as the right. And basically, the reason for this is you're going to pass in the lowest value child, right? Because then you're going to compare that lowest value child to the parent to see if things need to be swapped. And so that's effectively what it's doing. It's comparing keys at this point. So the self._data right over here has a key of 0, which is going to be lower than the left, which has a key of 4. So now you're going to have the small child is going to equal key 0. And now you're going to be comparing the data of the small child, which is 0 again, right? And the data of J. So here on the upper left of this watch screen where my cursor is, you see that the actual key of the parent is 5 and the key of the right child is 0. So that means that the min order property is not maintained, so it needs to perform a swap operation. So then it swaps those values around so that the parent becomes the left-hand child, and the left-hand child becomes the parent. And then it's going to correct itself downwards. Now that you replaced that parent that was larger than its child, it's going to now compare downwards from that position that now that parent value is located, if that makes any sense. It's a bit confusing, but now it's going to find that the position of that child doesn't have anywhere to go. It's going to be out of bounds, and so it knocks itself out because there aren't enough values in that array for those comparisons. And so what it's going to do is it's then going to go to the next index position downward, so it's going to start going through the index position 3 and doing all these comparisons. And what will happen is as you get higher, it's going to continually, recursively, whenever it has to make a switch, it's going to continually downward, recursively go through this down heap and compare things as you go. And you're continually comparing the left and the right children as well, until what you find is that after all is said and done, everything is organized properly. And so hopefully this overview of heaps was beneficial, and that this implementation of a min heap utilizing an array structure was enlightening. Again, Grover, Blue Collar Codes, episode 30. Thanks for joining.